Okay, this is video I6, day 2 of optimization, and I'll rewrite the problem right here. It's going to take a lot of space, so I'll probably write a little smaller. So problem 2. What should the height and radius of a cylindrical can be in order to minimize the material needed if its volume must be 1,000 cubic centimeters. Okay, and so we'll draw a little picture of a can, probably completely unnecessary. Here we have a height, here we have the radius, and we know neither. The one thing we do know is that the volume is that big. And I gave you these. Okay, the volume of a cylinder is the base area, the pi r squared, times the height. Okay, and we know if we're trying to minimize the material needed, what we're looking for is the smallest value of the surface area. Okay, that would give us the minimum amount of tin or whatever this is made out of. And the surface area formula, it's the area of the two bases plus this lateral surface area. And so it's 2 pi r squared meaning the area of that circular base, plus the lateral surface area, which is the circumference times the height. So 2 pi r times h. So this is what we're trying to minimize. The problem with this equation, though, is that we are dealing with two different variables, the r and the h, and we want to eliminate one of them. And it's probably going to be easiest to replace the h in terms of r. To do that, I'm going to go back to this equation. I know that my volume has to be 1,000. I can solve this for h and then substitute it right there. So h is 1,000 divided by pi r squared. So I can rewrite my surface area formula. It's 2 pi r squared plus 2 pi r times that. And honestly, I don't want to derive it yet. I want to try to clean it up if I can. So let's see what I have. I have 2 pi r squared. Okay, these pi's reduce. One of the r's will reduce. And so up top I have 2,000 over r. So here I have the surface area in terms of the radius. And if you wanted to, you could actually enter this into your calculator so you'd get a sense of what we're looking at. The curve looks something like this if you don't really care to do that. But we will get a minimum area. Don't forget, you could verify that this is a minimum when the slope is 0 and not a maximum by making a sign chart with the derivative, but I'm going to skip that part of this problem. Just know that you can do that. All right, so now I want to derive this with respect to r, and so I'll do that over here. I get s prime. Okay, my first term is, so there's my variable. It's just a power function. So I get 4 pi r. Okay, here, this is like 2,000 r to the negative first. So I get minus 2,000 r to the negative second, so I'll put it like that. So here I have the derivative of this curve, and I'm interested in when it's equal to 0. Okay, so I think it's probably easiest if I write this as a actually, it'd probably be easiest if I just multiply everything by r squared. And I'll get 4 pi r cubed minus 2,000. Multiply 0 by r squared, I still get 0. Now I'll add my 2,000 to both sides. Divide by 4 pi. And I get a nasty answer. But that's only half of the answer. I'll leave it like that. This would approximately be, if you put it in decimal form, about 5.42 centimeters. That's probably the answer that you'd want to give if your boss told you to do this. It would not be interested in that. But we want to also now find the height. Okay, and to find the height, I have a formula for the height right here in terms of r. And so I have h is 1,000. This is going to get terrible. Pi times this squared. Okay, and so I have, this is raised to the 1/3 power. Probably best to write it like this. So I'm going to square that. Remember, it was raised to the 1/3, and squaring it now would be raised to the 2/3. And interestingly enough, the height is exactly twice the radius. In other words, the diameter and the height would be the same. Okay, so that's our problem for today, and then I'm going to give you kind of a challenging problem now. Okay, I want you to try problem 3, and I'm going to try to hide what you don't need. I'm actually going to give you very little on this, and this takes a lot of creativity to do. Just go ahead and read problem 3. So I'll read it to you because I know my handwriting isn't all that good. A rectangle is inscribed in a semicircle with a radius of 2. What is the area of the largest such rectangle? Good luck, and we'll do this tomorrow.